Bismillahirrahmanirrahim. Assalamu alaikum dear students. This is your instructor Anisa Nawaz from Department of Physics. This is our lecture number 20 from chapter number 2, Vectors and Equilibrium. In the previous lecture, lecture number 19, we have discussed about some numerical problems related to dot and cross product of vectors. And after listening to today's lecture, you would be able to explain what is torque or moment of force, and you will also explain the factors upon which torque depends. You will understand that what is torque and what are the factors upon which torque depends. Okay, so torque, basically it is having another name, moment of force. Torque is having another name which is known as moment of force. The word moment is used for the turning effect. Whenever we are having turning effect, we will say that that is basically moment of that particular quantity. So sometimes the question arises in our mind that how does force create rotation? For example, if we are opening a door, we are applying linear force. We are pushing or pulling the door and door is rotating. So how is this thing that the force is creating rotation? What is the factor which is creating rotation? So we will discuss that. So that factor is basically torque. Okay, so if you are having motion in which an entire object moves is called translation. Translational motion, when the entire object is moving, like if we are pushing the ball, then it will start translational motion. And motion in which an object spins is called rotation. If this ball is rotating now, the point or line about which an object turns is its center of rotation. So if we say that if we are pushing the ball from here and it is moving, so this type of motion is translational motion. And if we are pushing we are applying force on this ball in such a way that it started rotation. Okay, it is spinning, so this type of motion is known as a rotation. Okay, so an object can rotate and translate. It can both rotate and translate. It depends that how we are going to apply the force. So force, what is force? Basically it is the action that creates changes in linear motion. It is the action that creates changes in linear motion. If there is no torque, then force alone will create changes in linear motion. For rotational motion, the same force can cause very different results. Okay, we are applying same force, but what is happening? The point of application is different. The way we are applying the force is different. That's why the same force can cause very different results. So what we can say, a torque is an action that causes object to rotate. Okay, force is creating linear motion while torque is causing objects to rotate. A torque is required to rotate an object just as the force is required to move an object in line. Okay, so why torque is needed? It is needed to rotate an object. So if we are going to give the formal definition of torque, how we are going to define the torque? Okay, torque or moment of force can be defined as turning effect produced in a body about a fixed point due to applied force is called torque or moment of force. Okay, the turning effect produced in a body about a fixed point. Like if we are applying the force, we are having this spanner and we are applying force over here. Okay, we are applying force due to which this spanner is rotating. So this turning effect produced by the applied force is known as torque. Okay, and keep this in mind that if an object is moving with uniform motion, like if a fan is already moving with uniform velocity, that is not the torque. Torque is only causing the motion, rotational motion to start or to decrease that. It must produce some effect. Okay, so we say that when we are switching on the fan and it start rotating, that effect may be known as torque, but when it is moving with uniform velocity, that effect is never ever known as torque, because it is the turning effect produced in a body about a fixed point due to applied force. This is basically torque or moment of force. So when we are applying force on this spanner and it is causing the spanner to rotate, this effect will be known as torque, turning effect produced in a body about a fixed point. Okay. So applied force F can act at an angle theta with respect to the position vector r locating point of application of force. Okay, so basically if we say that we are applying a force, let's say we are taking an example of door. This is top view of a door. We are applying a force on the handle over here. Okay, so this force is acting at an angle theta with respect to position vector r. What is this position vector r? It is basically the distance between the point about which the object is rotating and the point at which force is applied. This position vector r is basically the distance between the point about which the object is rotating. In this case, this is hinges of the door. Okay, so this is basically the point about which the door has to be rotated, and over here we are applying the force. So distance between these 2 points is basically the position vector r. Okay, so if we are taking the cross product between this position vector r and the applied force F, then we will get torque. The cross product between position vector r and force tau is equal to r cross F. So this equation is representing the torque, cross product of position vector r and the applied force. What is position vector r? Distance between the point about which the object is rotating and the point where the force is applied. Okay, so this is r cross F, and we have already discussed about cross product, so we can write this equation as tau is equal to rf sine theta n hat. Okay, so this n hat is giving us the direction of tau, rf sine theta is the magnitude of torque. So torque is created by force, but it also depends on where the force is applied and the point about which the object rotates. Okay, torque, it is created by force, but there are obviously some factors on which the torque is dependent. It is dependent upon where the force is applied, the point where you are applying the force and the point about which the object is rotating. These 2 points are also important. Okay, for example, a door pushed at its handle will easily turn and open, but a door pushed near its hinges will not move as easily. The force may be the same, but the torque is quite different. You can do it practically as well. You can push or pull the door at its handle, it will be opened easily, but if you are pushing the door near its hinges, it will not move so easily. Okay, it will not be opened or closed so easily. So it means that we are applying the same force, but point of application of force is different, so it is causing a difference. Okay, the torque produced is different because the point of application of force is different, and the distance between point of application of force and point about which the object is rotating is different. So these 2 are the factors upon which the torque is dependent. That's why we have given that expression tau is equal to r cross F. Torque is dependent upon applied force and it is dependent upon the distance between point of application of force and the point about which the object is rotating. Tau is equal to r cross F. Okay, so what if force is at some angle? If we say that we are pushing the handle at some angle, we are not pushing it straight away, we are not pushing or pulling it at 90 degrees, then what will happen? We are applying force at some angle, then what will be the torque produced? So you can say that this is basically the point about which the door is rotating. It is also said as pivot point, and if it is the line about which the object is rotating, then it will be known as axis of rotation. So this pivot point basically r position vector, distance between this pivot point and the point of application of force. And what if the force is applied at some angle? It is not making an angle of 90 degrees. Okay, then what will happen? Just as we did in the cross product, we will resolve this force. Okay, we will resolve this force into components. How? We will check this out. The applied force is not always perpendicular to the position vector. It is not necessary that the applied force is perpendicular to the position vector. It may be at some angle to the position vector r. The component of the force perpendicular to the object will cause it to rotate. We will see how. When the force is parallel to the position vector, no rotation occurs. You can see this, that if we are pushing the door in this direction, will there be any rotation? No, there will be no rotation caused in the door. You can do it practically, perform this. If we are pushing the door in this direction, we are basically applying the force parallel to the position vector r. It means that tau is equal to Rf sine of 0 degrees. That will give you 0 magnitude of torque. Okay, so we will be having no resultant torque. If force is applied parallel to position vector, no rotation occurs. But when the force is at some angle, the perpendicular component causes the rotation. You can see here, if now the force is applied in this direction, what will happen? We will resolve this force into vertical and horizontal component. This horizontal component of force, F cos theta, you can see it is parallel to r. It is causing no rotation. This component, horizontal component, is making no difference in producing the torque. Which component is effective? This F sine theta. Basically, this F sine theta is responsible to produce the rotation. So this the rotation will be produced in the direction of the vertical component of this force. Okay, you can see the rotation will produce either in this direction or in this direction, dependent upon the direction of applied force and the vertical component of the force. Okay, so we will say that, that's why we can say that torque is the cross product between r and f, because vertical component is the effective component over here. F sine theta is the effective component of force over here, which is producing the torque. So when force is applied parallel to position vector, no torque is produced. When force is either perpendicular or at some angle to r, then we will be having some rotation, and that turning effect, that rotation will be known as torque. So let F be a force acting on an object and let R be a position vector from a rotational center to the point of application of the force. The magnitude of the torque is given by tau is equal to Rf sine theta. This symbol, this is not T, basically it is tau, a symbol, TAU, tau. Tau is basically the symbol of torque. So this tau is equal to Rf sine theta. Okay, the symbol of torque, which is tau, Rf sine theta. This is representing the magnitude of the torque. Okay, if theta is 0 degrees or 180 degrees, then what will happen? It means force is parallel to position vector and the torques are equal to 0. And if theta is 90 degrees or 270 degrees, magnitude of torque attain to the maximum. Okay, so what will be happening over here? If angle between r and f is 0 degrees, what will happen? Torque is 0. And if angle is 90 degrees or 270 degrees, then magnitude of torque is maximum. Tau is equal to Rf sine theta. Okay, so what is center of rotation? Basically the point or line about which an object turns is its center of rotation. If it is a point, it will be known as pivot, and if it is line, that will be known as axis of rotation. So the point or line about which an object turns is its center of rotation. For example, a door's center of rotation is at its hinges, and a force applied far from the center of rotation produces a greater torque than a force applied close to the center of rotation. Okay, so what will happen if we are considering the example of the door and we are applying the force over here. You can see if force is applied far from the hinges, then what will happen? We will be having a greater R, and we know that torque is directly proportional to R. Tau is equal to R cross F. So torque is directly proportional to R. If force is applied far from the center of rotation, a greater torque will be produced, and if it is applied near to the center of rotation, less torque will be produced. Okay, so what will happen? Torque is directly proportional to R. Okay, so the torque is created when the line of action of force does not pass through the center of rotation. Well, what is line of action of force? The line of action is an imaginary line that follows the direction of a force and passes through its point of application. Okay, so you can see over here, if we are applying, we are again taking an example of spanner. Okay, you can take any object over here, but we are taking a general example of spanner most of the times because it is easy to understand. If this nut which is being rotated, it is center of rotation, or you can say pivot point, and we are applying force in this direction. Okay, we are applying force in this direction, then we will draw an imaginary line along the direction of this force. We will extend this force in backward and forward direction. So this complete line, okay, this complete line is known as line of action of force. This imaginary line is known as line of action of force. Okay, it is basically following the direction of a force, and it is passing through the point of application of force. So force is applied over here, and if we are extending it in backward and forward direction, that will be known as line of action of force. Okay, so this imaginary line is known as line of action of force, and if this line of action of force is passing through the center, then what will happen? There will be no torque. Okay, like if we are applying force on this nut, okay, if on the spanner we are applying force over here, then what will happen? It will not cause any rotation. Or if we are applying force parallel to this spanner, then what will happen? Line of action of force, if we are extending that force in the backward direction, that line of action of force will pass through the center of rotation. Then what will happen? Again, no torque will be produced. So if line of action of force is passing through the center of rotation, there will be no torque. Keep this in mind. There must be some distance between the line of action of force and the center of rotation. Okay, and it should not pass through the center of rotation to produce the torque. The component of the force F cos theta has no tendency to produce a rotation. We have already discussed this thing, that F sin theta is responsible to produce a rotation. Okay, so we can say that magnitude of torque is equal to Rf sin theta, okay, which can also be written as Fd. What is this d now? We can write it as, instead of Rf sin theta, we can write it as Fd. Okay, for example, let's say we are again having an example of spanner over here. Let's say force is applied over here, okay, and it is at some angle to the position vector r. Then what we can do, we can resolve this force into horizontal and vertical components. Then what we can do, we can multiply this position vector with this vertical component of the force to get the required torque. Okay, and if you are taking the example of this door, again force is applied at some angle, then what we have to do, we will resolve the force into its components, and then we will multiply this vertical component with this position vector. That will give us the torque Rf sin theta. But we are having another approach of calculating the torque. Okay, we are having two approaches to calculate the torque. First one, which we are discussing up till now, that if we are having the force which is applied, we will check out that at which angle force is applied. If it is parallel, then torque will be 0. If force is perpendicular, then we will simply write it as Rf sin of 90, which will be Rf. But if force is acting at some angle, we will resolve the force into horizontal and vertical components. Then we will multiply a vertical component of force with position vector. This is what we have discussed up till now. We are having another approach due to which we are writing it as tau is equal to Fd. Now what is this d? Basically d is the you can say moment arm. it is giving a name, moment arm or lever arm. We will discuss it. What is this D basically? Which it is representing the second approach to interpret torque. That second approach is basically associating sine theta with R instead of F. Up till now we have resolved the force into its components. Then now what we can do, we can find out the line of action of force. We will draw the line of action of force, and then we will drop a perpendicular from that line of action of force to the pivot point or center of rotation. The perpendicular distance between the center of rotation and the line of action of force is known as moment arm, which is represented by D. D is equal to R sine theta. Okay, in general words you can say that we are now resolving R into its components. Position vector is being resolved into its components, but in simple words we can say that we are just taking perpendicular distance between line of action of force and this pivot point or position vector R. Okay, so that will give us R sine theta. Okay, so in your book this figure is given. You can see over here we are having two approaches. That if we are having force applied at some angle, what we can do, we can resolve that force into its horizontal vertical components. Then we can multiply R with F sine theta. So torque will be R F sine theta. Okay, and the second approach is that if we are having a force applied at some angle, then we can find out the perpendicular distance between this R and line of action of force. Okay, we can find out this perpendicular distance from pivot point to the line of action of force, which will give us R sine theta. Okay, and we will multiply force with this vertical component of R, F R sine theta. We will get the same result. It doesn't matter which approach we are using, both are correct, but most of the times this approach is used, in which we are finding out the perpendicular distance between pivot point to the line of action of force, because this is, you can say, in a way direct method. We can simply multiply the applied force with D, moment arm. Okay, this perpendicular distance is known as moment arm. Okay, D, it is represented by D, moment arm, R sine theta. D is equal to R sine theta. Okay, so if we are going to define the moment arm D is the perpendicular distance from the axis of rotation to a line drawn along the direction of force. Okay, so D is equal to R sine theta. What is D? Perpendicular distance from the axis of rotation to a line drawn along the direction of force, which is basically line of action of force. Okay, so moment arm is simply perpendicular distance between axis of rotation to the line of action of force, nothing else. It should make an angle of 90 degrees. Okay, we have to drop a perpendicular basically from the line of action of force to this axis of rotation. So moment arm is defined as perpendicular distance from axis of rotation to the line drawn along the direction of force. Okay, so D is equal to R sine theta. It is moment arm, which is also known as lever arm. Moment arm or lever arm, it is perpendicular distance between line of action of force and the center of rotation. And why it is known as lever arm? Because you know the principle of lever, that if we are having a longer lever, then we have to apply less force. That's why we are using this word over here, that if moment arm or lever arm is longer, then we have to apply less force to produce the torque. Okay, you should know, you should have this concept of moment arm, that's important. Okay, so the lever arm of a force, again same thing, that if force is applied some angle, in the case of the spanner, then what we will do, we will extend this force and we will drop a perpendicular from axis of rotation to that of this line of action of force. That will give us lever arm. Okay, so the torque relative to origin is defined to be the cross product of lever arm, moment arm and force vectors. Okay, so now we can define torque in other words, that it is the cross product between the moment arm and force. Okay, it is the cross product between lever arm and the force, and we can say it measures the tendency of the body to rotate about the origin. Okay, it measures the tendency of the body to rotate about the origin, and the direction of the torque vector indicates the axis of rotation. So the direction of torque vector, it is basically direction of torque vector, we can find it out by right hand rule. It is indicating the axis of rotation, axis about which the object has to be rotated. So same definition with different words, that cross product of lever arm, moment arm and force vectors. Okay, so if we are checking out the magnitude of this cross product, then we can also say it is equal to tau is equal to RF sin theta, which is equal to FD. Tau is equal to RF sin theta, magnitude of this cross product, which can also be written as FD, multiplying force with the moment arm. Okay, so what we can say over here, torque created by force, you can see that the line of action of force is given over here. We are applying force, and this is center of rotation about which the nut is rotating, and the perpendicular distance between this axis of rotation and moment line of action of force is known as lever arm or moment arm. Torque is a vector quantity, obviously, as it is the cross product between two vectors, and cross product of two vectors gives us a vector quantity. So torque is a vector quantity, and its magnitude is given as tau is equal to RF sin theta, which is equal to FD, where D is moment arm. Okay, so it could be any body, any, you can say, random shape. It may not be a spanner or door. You can take any rigid body, any random shape on which we are applying the force, and if we are applying force in such a way that it is at some angle to the position vector, let's say this O is the point or pivot point, the point of rotation, center of rotation, and force is applied on this point, then what will happen, this body will start rotating in this direction. Okay, it will start rotating in this direction. It is having tendency now to rotate in this direction because we are applying force at some distance from the center of rotation, and this force is making some angle. Okay, it is not parallel to this position vector, it is making an angle with this position vector, so it will be having tendency to rotate, and it is rotating in anti-clockwise direction. You can see over here this object is having a tendency to rotate in the anti-clockwise direction. So it could be any rigid body. It is not necessary that we are taking a spanner or a door or something like that. The units of torque are Newton meters. Okay, because tau is equal to FD, so force is having unit of Newton, and distance is having a unit of meter, SI unit of meter. So unit of torque are Newton meters, and you can also find the dimensions of torque as well from its formula if you want to do it. A torque of 1 Newton meter is created by a force of 1 Newton acting with a moment arm of 1 meter. This is the definition of 1 Newton meter. It is created by a force. Torque of 1 Newton meter is created by a force of 1 Newton acting with a moment arm of 1 meter. Okay, so what we can say, if 1 Newton force is applied at a distance or moment arm of 1 meter, then a torque of 1 Newton meter is created. Okay, so again same example of a spanner. You can see we are applying force. If this force is 1 Newton and distance is 1 meter, then a torque of 1 Newton meter will be created. Okay, now we can conclude this thing that we are having certain factors upon which torque is dependent. There are 3 factors that determine the effectiveness of the force in producing torque. First, the magnitude of the force. Okay, how much force is applied. Second, the position of the application of the force. Okay, that where the force is applied. Okay, first the magnitude of force, then the position of the application of the force, and third one, angle theta between applied force and the position vector. These 3 are the important factors upon which torque is dependent. Okay, magnitude of force F, position of application of the force which is giving us position vector r, and third thing, angle between force and position vector, again justifying the definition of torque. Okay, it is dependent upon r, f and theta. So tau is equal to rf sin theta, because perpendicular component is responsible to produce the rotation. So these are three factors which determine the effectiveness of the torque. Okay, so over here you can see the force is applied, if it is applied in this direction parallel, and if this force is applied, again you can see that the force is applied in at the center, then what will happen? You can see over here that this force is applied over here, it will produce greater torque. Okay, and if the same force is applied at this point, now r is decreased, then what will happen? It will produce lesser torque. Okay, and if it is applied parallel to the position vector r, then there will be no torque. Okay, so that was about the factors on which torque depends. You have to learn all these three factors. And torque is also having direction, whether it is applied in the it is producing rotation in clockwise or anti-clockwise direction, then what will happen? We have to give the signs accordingly. Okay, if the turning tendency of the force is counterclockwise, the torque will be positive, and if the turning tendency is clockwise, the torque will be negative. By convention, we are you can say supposing this thing, that if turning tendency or if the rotation is counterclockwise, it is in anti-clockwise direction, then torque is taken as positive. We have to place a plus sign with torque. Okay, this is just a convention, that if torque is producing a rotation in anti-clockwise direction, then we have to put a positive sign with that torque, it is positive. And if the turning tendency is clockwise, the torque will be negative. You can see over here, if clockwise direction is there, torque is applied in the clockwise direction, then this torque will be negative. Okay, so by convention, anti-clockwise direction is anti-clockwise torque is positive and clockwise torque is negative. Okay, and torques can be added and subtracted. If more than one torque act on an object, the torques are combined to determine the net torque. Okay, you can see over here that if two forces are applied on the same body, then we can add these two torques. Okay, let's say that this is you can say center of rotation, and one force is applied at this much distance, so it is producing a torque in, you can see it is in clockwise direction, so this torque will be negative. Okay, so clockwise torque is negative. So if we are finding the torque over here, that will be negative, and if we are finding the torque of this force which is in anti-clockwise direction, this torque will be positive. You can see the torque due to this force A is positive and the torque due to this force B is negative. Okay, and how this torque is created? By multiplying force with the distance. Tau is equal to F into D, force into distance, that gives us the torque. Okay, and if it is in clockwise direction, that will be negative, and if the torque is acting in the anti-clockwise direction, that torque will be positive. And more than one torques can be added. If you are having different torques, they all can be added. Okay, so if we say that we are having a rigid body, any random body in which on which two forces are applied, one force in this direction and one force in this direction, this O is center of rotation, this force F1 is causing anti-clockwise rotation, so this torque will be positive, and this force F2 will be causing clockwise rotation, that torque will be negative. So we will add these two torques, but when we will put their magnitude, one will be with positive sign and one will be with negative sign, anti-clockwise with positive sign and clockwise with negative sign. Okay, so keep this in mind, that whenever the force is causing the object to rotate in anti-clockwise direction, we have to put a positive sign with the magnitude, and if it is causing rotation in clockwise direction, we have to put a negative sign with that torque. And rate of rotation of an object does not change unless the object is acted on by a net torque. So whenever a torque is applied, rate of rotation in object change. Okay, so if there is no net torque, then what is happening, there will be no change in the rotational acceleration. Okay, so torque is must to produce a change in rotational velocity of an object. Okay, so if we say that direction of torque, that can be determined by right hand rule, because it is basically an example of cross product. So just like we have calculated the direction in the cross product, we can calculate the direction of torque as well. Okay, so the magnitude, again same thing, magnitude of the torque is equal to the area of parallelogram determined by R and F. So F is applied over here. So first step to cross multiply these two objects, these two quantities will be, we have to join them tip to tip. F will be placed over here, then we will curl the fingers of right hand, and we will see that the thumb is pointing in this direction, which is giving us the direction of torque. It is basically telling us about the axis of rotation. So R cross F will give us the direction of torque, which is perpendicular to the plane containing R and F, just as in the case of cross product. Okay, so the direction of the torque vector indicates the axis of rotation, which we have already discussed, that if we are finding out the direction of torque by right hand rule, the thumb will indicate us about the direction of axis of rotation. Okay, and if we want to find out maximum torque with minimum force, to get the maximum torque with minimum force, the force should be applied in a direction that creates the greatest momentum. Okay, so what is happening over here, we have to apply the force in such a way that it is having greatest momentum. So with minimum force we can apply maximum torque. And application of torque, you can say the everyday tools which we are using in daily life, all these which need spinning, rotating or turning, so all these are having you can say application of torque basically. Okay, the rotating of tap, opening nut with a spanner, opening the cap of the bottle, all these things require torque. So in this book, in your book, you are having this figure. We are having an example of a spanner. Okay, so this is the nut. Okay, this is nut, and we are using a wrench. We are using a wrench to turn this nut. Okay, so what we will do, we are applying force in this direction. We are applying force in this direction at some angle with the position vector R. You can see over here, first approach is explained, that we are resolving this force into vertical and horizontal component. Okay, horizontal component of force and vertical component of force. You can see that this horizontal component of force is producing no effect in rotation. Okay, it is not effective in producing rotation, only the rotation produced is due to this vertical component. This force is resolved into horizontal and vertical components, and rotation is produced due to this vertical component of the force. Okay, so this was the first approach in which we have resolved the force. If we are using the second approach of moment arm, then what we will do, we will extend this force. We will draw the line of action of this force, and then we will draw a perpendicular. We will draw a perpendicular from the axis of rotation to that of this line of action of force. These two should be making an angle of 90 degrees. Okay, perpendicular distance from axis of rotation to the line of action of force. This will give us the moment arm, which is equal to R sine theta. So either you can multiply F sine theta with R, or you can multiply F with R sine theta. Both will give us the same result. Okay, so these are the two approaches which are used in your book. So if you are going to write down this torque as a long question, then how you can do it in different ways, but you can say just a layout is there. You can first write down the definition of torque, then equation, then unit of torque, figure, explanation, moment arm or lever arm, interpretation of torque, two different ways which we have already discussed, resolving force and drawing the moment arm. Okay, you have to write those two approaches with subheadings. Then you can write down the magnitude of torque, direction of torque. Okay, all these things can be written under separate headings, and the factors on which torque depends. You can write all these things over different main headings. Okay, so you can make your notes over these topics. So I would like to end my lecture with this quote. My message to you, it is the quote of Quaid-e-Azam Muhammad Ali Jinnah. My message to you all is of hope, courage and confidence. Okay, so never lose hope, do your best and be confident in achieving your goal. Inshallah, Allah Almighty will help you all. Okay, so that was all for today's lecture. In next lecture, inshallah, we will discuss about moment of a couple and concurrent forces. Till then, thank you so much.